Hi everyone, in this video we are going to solve one problem about linked bodies. We have two bodies in an inclined plane, now in these conditions, a pulley, and the surface has friction. You receive the angle, and the idea is to find the acceleration and the tension of the rope acting on each object. Okay, we receive the masses that are 1,500 kilograms for one, for mass 2, 800 kilograms, and the dynamic and static friction coefficients. The angle, this angle is 50 degrees, and we have two items to solve the problem with friction, without friction, and then we are going to add frictions with these coefficients. Okay? Well, the first step is to analyze the masses. Sometimes from the values that we receive, we understand the possible motion of the system. In this case, mass 1 is higher, is almost twice the mass 2, 1,500 kilograms. So we suppose that the system is going to accelerate in this direction, anti-clockwise in this case. So the first step is to state the frame of reference. If we understand that the system moves clockwise, we are going to say that we consider positive upwards for the mass 2 and positive downwards for mass 1. And why? The idea is that both accelerations have the same sign. Suppose that you solve the problem, and at the end of the you solve the system of equations and the acceleration is negative. Well, that's not a problem. That means that your hypothesis that the system is accelerating clockwise, anti-clockwise in this case, was wrong, and the system accelerates clockwise. But well, here, from the values that we receive from the masses, we assume that the system is going to accelerate anti-clockwise. Okay, now we analyze the forces. On 1, we have weight and the tension of the rope, and nothing else. Okay, on 1, the tension because it is connected directly with the rope, and weight, the attraction due to gravity. What happens with object 2? Object 2 has the tension, it has weight, it has a normal force because of the contact with the surface below, and it has friction. But in the first statement, we are going to solve the problem without friction. Typically, friction is going to point in this direction, opposite to the tendency to slide. Okay? Well, the free body diagram without friction is tension, normal, and weight. Weight, in this case, weight 2. Here we have weight 1, weight 2. How do we proceed with the weight? Well, what we are going to split the weight into weight 2 in y and weight 2 in x. And we notice that the angle, this angle, is equal to this angle, alpha. So here we have weight 2, we are going to obtain weight 2 in y, weight 2 in x. And once we have these two contributions, we forget the real weight. No? Okay. Well, we are going to write the system of equations. Remember that for mass 2, this is mass 2, this is mass 1. Positive is upwards, and for 1, positive is downwards. So we write the equations of motion in the direction of motion and in the perpendicular direction for the case 2, for mass 2. So for 1, we have weight 1 minus tension, now weight 1 is positive, is equal to mass 1 times acceleration. For 2, we have in the direction of motion tension minus the force that is opposite or in the negative direction is weight 2 in the x coordinate, and that's equal to mass 2 times acceleration. We in the perpendicular direction, because we have a perpendicular direction here, we have normal minus weight y, so weight 2 in y now, and that's equal to 0, because the acceleration, if it is present, is parallel to the surface. but not perpendicular. So here we have a 0. So the normal is equal to the weight 2 in the y coordinate. In a minute we obtain the values weight 1, weight 2, weight 2 in x, weight y, or weight 2 in y. So here we have a system of two equations, 1 and 2. One possibility to solve the problem and to find the acceleration and the tension is to add the equations, and we are going to obtain the acceleration in the first step, and then we replace acceleration here, here, or here, and we obtain the tension. Okay, but before solving the system, we are going to obtain weight 1. Weight 1 is mass 1 times gravity, so it is 1,500 kilograms times 10 meters per second square, so the weight is 15,000 Newton. That's weight 1. Okay, weight 1, 15,000 Newton. What happens with weight 2? Weight 2, the whole weight is mass 2 times the acceleration due to gravity. So we have 800 kilograms times 10 meters per second square, and we obtain 8,000 Newton. Okay, that's weight 2. But as weight 2, as mass 2 is in a plane, we have to split the weight into y and x. So we are going to use sine and cosine. What happens with weight 2y is the adjacent cathode, so we use cosine. Cosine of 50 in this case is weight 2y divided by the weight 2. Now that is the hypotenuse of this triangle. Okay, so weight 2 we know the value, 8,000 Newton. We pass it multiplying, so we have 8,000 Newton times cosine of 50. Cosine of 50 in a minute is 50, 0.64. Okay, 0.64. That's weight 2 in y. So weight 2 in y is 0.64 times 8,000. Sorry, 0.64 times 8,000. The result is 5,120 Newton. That's the weight 2 in y. That's useful to find the normal force. In this case, in the first item, we don't receive the question obtain the normal force, but it is important for the second part when we want to obtain the friction, and the normal force doesn't depend on the value or on the conditions of the exercise. It doesn't depend on friction present or not. Okay. Well, and what about the weight in x? In this case, it's the opposite cathode, so we use sine. Sine of 50 is equal to weight 2 in x divided by the weight 2. So weight 2 in x is 8,000 Newton times sine of 50. Sine of 50 is 0.77 or 766, 0.77 times 8,000. The result is 6,160 Newton. Okay, that's the weight in x. Okay, well, now we are going to solve the system. Now we come back to the system in the direction of motion. One possibility is to add the equations. So we have weight 1 minus tension plus tension minus weight 2 in x. We are adding weight 1, tension minus tension, tension minus weight 2 in x. Now everything that is in the left side. And in the right side we have mass 1 times acceleration plus mass 2 times acceleration. Well, as we are using ideal ropes, no, the tension exerted on 2 in absolute value is equal to the tension on 1. So tension 1 and tension 2, they are equal. So we can cancel them. Therefore, we didn't use numbers for each tension. And we have here weight 1 minus weight 2 in x is equal to mass 1 times acceleration plus mass 2 times acceleration. Mass 1 is 1500 kilograms times acceleration. Mass 2 is 800 kilograms times acceleration. And we know the value of weight 1, we have it here, now we obtained it before, the same for weight 2 in x. So 15,000 Newton minus 6160 Newton is equal to 1500 plus 800, so 2300 kilograms times acceleration. And now we are going to subtract here and divide by 2300. 1 second. And the result will be before we divide, the result is 8840 Newton divided by 2300 kilograms. So the acceleration in the system without friction is 3.84 meters per second square. Okay, and if you want the tension, you replace in any of these two equations. For example, the second one, in the second equation, we have tension 2 minus weight 2 in x is mass 2 times acceleration. So remember that we obtain a positive value, which is the idea is that we use the correct, not the correct, you can use any reference frame, positive upwards or positive downwards, but we assume that the system was accelerated anti-clockwise. Therefore, we obtain a positive value, which is coherent with our hypothesis. So tension 2 is equal to mass 2a, 800 kilograms, times acceleration, we know the value, now we replace, plus weight 2 in x. So in the x coordinate, 800 times 3.84, 3.84 times 800, that is 3072 newtons, plus weight 2 in x, which is 6160 newtons. So the final value is 9232 newtons. Okay, that's the tension. So now we solve the first item. Okay, now the idea is to analyze the problem with friction. Okay, so we are solving like two possible different exercises in one. Okay, what happens if it has friction? Or how do we analyze this problem? No, we have an object 2. There is, well, it is in contact now. One possibility is, okay, it can move here, and we have object 1. Okay, well, now in terms of the free body diagram or the analysis that we did before, okay, the analysis that we did before, we know that the system is going to accelerate upwards in the case of 2 and downwards in the case of 1. What is different now? The presence of friction. If the object 2, the tendency to slide is upwards, friction is here in the opposite direction. And the equation 1, the equation for the object 1 doesn't change. But in the equation 2, we have to add one force subtracting. So the new system, for 1, we have weight 1 minus tension is equal to mass 1 times acceleration. And in the case of the second one, we have normal, tension, now friction. We can say weight 2 in x, weight 2 in y. The real force is the weight, but we have the contributions in each direction. And here we have weight 1 and tension. So the equation in the direction of motion for object 2 is tension minus friction minus weight 2 in x is equal to mass 2 times acceleration. And what happens in the perpendicular direction? We know that the normal minus weight 2 in y is equal to 0, but we have the value of the normal. it was weight 2 in y. Weight 2 in y is 5,120. 5,120 Newton. Okay. Well, that's important to obtain the maximum static friction, but we are going to analyze something else before we keep on working. What happens when we have friction? One possibility is that the object doesn't slide at all. So what is this? Is to have an acceleration that is 0. So if we sum and we assume that the object doesn't slide, we are going to obtain the friction that is needed to maintain this system at rest. So that's a hypothesis, no? Hypothesis, acceleration 0. Okay? So in this case, weight 1 minus tension is 0. So tension should be equal to weight 1. And we know that is 15,000 Newton, okay, from the previous exercise, the weight 1. If tension is 15,000 Newton, in the second equation, we have 15,000 Newton minus friction minus weight 2 in x. Weight 2 in x is 6,160 Newton, okay, equal to 0. Okay, so now friction must balance the difference between the tension and the weight in x. So friction, we pass it to the right side, and it's 15,000 minus 160. Sorry, it's my cat that is disturbing a little bit. 840 Newton. That's the friction that we need to maintain the system at rest. Okay, but we know that each surface has a maximum possible friction, because friction can be lower or equal to the maximum static friction. Now we are under static conditions in this hypothesis. The object doesn't slide and acceleration is 0. What is maximum static friction? Is the static friction coefficient times the normal. So the normal, we have the value 5,120, and the static coefficient, well, we have it here at the very beginning. It is 0.6. So 0.6 here, 0.6 times 5,120 Newton. So 0.6 times 5,120 Newton, it is 3,072 Newton. So the static friction has a maximum possible value of 3,072. So it cannot provide the friction required to maintain the system at rest. So the system slides. Okay, and well, the system slides. So we have a object 2 is in motion. The same happens for 1, and we have the same system, but now we know that the friction is dynamic. Friction is dynamic or kinetic because the system slides, and the friction, when it is dynamic, it has a constant value of the dynamic friction coefficient or kinetic or friction coefficient times the normal. In this case, the kinetic or dynamic friction coefficient is given. It was 0.35. 0.35 times the normal. 0.35 times the normal, that is 5,120 Newton. So the dynamic friction is 5,120 times 0.35. 1,792 Newton. This is the value of the dynamic friction. And now we can solve the system, because we don't know the acceleration, we don't know neither the tension, but we know that the friction is dynamic. So we write again the system. 1 is weight 1 minus tension equal to mass 1 times acceleration. We write the equation for 2, which is tension minus friction, which is dynamic, minus weight 2 in x is the mass 2 times acceleration. Now we sum this equation, we cancel the tensions as we did before, we have the value of the dynamic friction we have the value of weight 1, weight 2 in x, and we sum mass 1 times acceleration plus mass 2 times acceleration. Well, the sum of them was 2,300 kilograms times acceleration. That's what we did before. We replace the value of the forces, we divide, and we have the acceleration. Weight 1 was 15,000 Newton. Dynamic friction is 1,792 newtons, and weight 1 in x, weight 2 in x is 6,160 newton. So the acceleration is this equation, 15,000 minus 1,792 minus 6,160 divided by 2,300, which is 3.06 meters per second square. Okay, we pass this one divided now, and that's acceleration. Okay, and again, when we want the tension, we can replace acceleration here or here, and we finish. In this case, if we use the first one, tension is weight 1 minus mass 1 times acceleration. Now we pass this one to this side, this one to this side, and tension is weight 1, 15,000 Newton, minus 1,500 kilograms times 3.06 meters per second square. So the tension is 15,000 Newton minus 3.06 times 1,500, which is quite close to 4,500, no? 4,590 Newton. We subtract, and we have the final value, which is 10,410 newtons. Okay, well, with this we finish this exercise. We solve the problem without friction. We assume, or to check if the system slides, we analyze what happens if the acceleration is 0. The force of friction that we need is lower than the maximum possible value that this surface can give us, that is the maximum static friction, so the system slides, and at the end we obtain the acceleration and the tension working with the same system, but understanding that the friction must be dynamic. Okay, well, goodbye.